for lunch. You made it. My name is Pratola, and I'm one of the, I guess, lone warrior statisticians in this group. But I do have something that all the physicists here will be very jealous of, and that is, so when I was a high school student, my favorite classes were computer science, calculus, and then chemistry and physics, sort of like equally. And I wouldn't say I was very good at physics, but I found it really interesting. But later on, I kind of discovered why I struggled with physics at the high school level, and that was because my teacher back then was a former PhD scientist from Chalk River, which was the lone, I guess, Canadian nuclear research reactor. And his name was Mr. Bond. Yes. So, yes, you should all be jealous now. So. All right, anyway, so today I'll talk to you about some of the work we're doing with the Bayesian Model Mixing and Tawaret, which is the software layer within the larger advanced software frameworks that we're developing. So I'll just give you I guess a brief overview, and then we'll see the talks by Alexandra and John, who will deep dive on the two methods that we have implemented right now. So of course, our usual kind of cover slide here about band, and so we're talking about this stuff here right now. And so I'll talk about a couple things. The main focus for this band camp will be these mean mixing methods, and these two here that we have available. But more generally, there's also density mixing methodologies that Dan and Kevin are working on. So maybe those will be ready for the next band camp. So that's sort of the kind of methodology side of the overview, and then we have the software interface, which is Tawaret, which is a Python code. So we'll see how that works. So a general sort of framework, and this is not the only way of sort of formulating a problem, but it's perhaps from a statistician's perspective, kind of the canonical way you might frame a problem when you have observational data and you're trying to fit a model to it. So you have some data y that is observed, and it depends on some p-dimensional input x. And this y that we're observing in the real world is an observation of some underlying, say, physics phenomenon that we are actually interested in, which is this unknown to us f-Dagger function of x. And so a kind of classic statistical approach is to embed this this unknown f-Dagger into a Gaussian observational data model. So the y's that you observe are re-centered at that f-Dagger, and then there's some, say, variance or variance covariance model accounting for the unexplained portion of the signal that you observe. And the problem, of course, is that we don't know f-Dagger, and we actually don't even know a good approximation of it. But the unique thing in this sort of model mixing idea is that we do know or can construct a fairly decent local approximation. And so that's sort of the unique thing here, is that we often have good local approximators, but not a good global approximator. Okay, so, but before we sort of dive into what that might look like a little bit, perhaps some motivation from history, so a bit of a back before the future kind of slide. If we ignore the locality issue in kind of mixing these models that we're interested in learning about, well, global weighting of models has appeared in the stats literature for a long time. So if we just think about global weighting, well, this is actually a fairly standard interpretation, actually, of Bayesian modeling, is that you're weighting things together to get adequate posterior distribution. And from a kind of model construction approach, a classic construction is the BMA, or Bayesian model averaging approach, where so you might have some probabilistic description of that unknown f-Dagger under some model MK, and then you combine, say, cap k of these things using scalar weights. And So these weights note that they're not dependent on any input, so they're global weights. And asymptotically, what this BMA machinery will do for you is eventually converge on the one model that is the truth. So the weights will go to 1, identifying exactly which model it actually is. Here's a more motivational picture describing the situation we have in band, or that we're interested in band. So here we have some true f-Dagger function, that's this gray, stark gray line here, which we don't actually typically know in reality. But we are able to construct good local approximators, and so here there's two approximators, this dotted line here, where you can see that the approximation is really good in the sort of, say, x greater than, I'm looking at an angle, so I don't really know, but x greater than maybe 0.4, something like that. So it's good out here are the large x's, but really poor elsewhere. And then we have also this dashed gray line here, right, which is really good at the small x's, so maybe x less than 0.15 or something, but it's terrible elsewhere. So we'd like to combine these two sources of information, which actually are physics-motivated models, to get at a good estimation or prediction for that underlying f-Dagger thing that we don't actually know. If you just apply DMA blindly, then you'll get something like this. This is the black solid line that we see here. That's the posterior mean of applying Bayesian model averaging, where you can't actually account for the fact that these models are only good in localized regions of the input space. So essentially what it does is it says, well, the way BMA works, it assumes that one of the models is right. And so when you turn that BMA crank, it ends up deciding that this model is quote-unquote right, which is clearly not a good answer. You really ever learned much more than what you knew before. So that's what we're trying to, I guess, get away from, is this inherent assumption of a global best model and shift to this idea of locally best models. So that's the framework. So we have these K models, say script M1 through script MK. And one way of sort of thinking about, what do we want to actually do with these models is maybe we want to do some sort of mean prediction, right? So for model L, we could have the mean prediction of our process is given by this f hat L. Okay. And then once we have this f hat L for all of our capital K models, then we could kind of repeat that idea of a simple Gaussian observational framework to mix these various models together. So we'll say our y's are Gaussian, but now we'll put the mean as being this linear combination, this weighted linear combination of those predictions from our cap K models and some variance covariance for the observational area. And then now we note that these weights are indeed indexed by the input. So we should be able to recover local weighting of these various predictions from our various physics models. And so the modeling stuff then, it sort of has like two layers to it. It has this first layer, which is given a model, right? So conditional on model ML, what is the quantity of interest that I'm estimating? Here we're just thinking about prediction, so f hat L is just the mean function, or the predicted mean function. And then the second layer is, well, how does that relate to the y's? And that's where the mixing actually comes in. So in this setup, we're trying to relax those constraining assumptions of the, say, BMA or classical approaches, in that we're saying, well, there's no single model in our set that adequately describes that unknown m-Dagger or f-Dagger that we'd like to learn about. But we kind of hope that a locally weighted combination of these models may actually represent that unknown m-Dagger really well. That would be like the best case scenario. Or, at the very least, a locally weighted combination of the models in the set will provide a better description of m-Dagger than any single model in the set will. And maybe we can identify where even all the models in our set locally don't provide a good prediction or don't provide a good description, and where in the open space that occurs. Density mixing, similar kind of idea, except that, so here we're doing the mixing in terms of the mean model of our data or our process. And then here we're mixing at the level of densities. So again, we have our K models with corresponding now densities. So P of Y given script MK. And then we might take the weighted combination of these densities to get at our mixed density model for quantity of interest. And the same sort of ideas are present here. We're trying not to assume a single best model. We're trying to assume that maybe a linear combination of models will represent the true M dagger adequately, or at least a weighted combination will do better than any single model would have. Okay. How's that? Am I going too fast, or is this? Any questions? Okay. So let's think about these weights, and there's a few different ways of both setting up and interpreting these weights. And I'll just talk about the two that we've sort of been looked at so far. So one is, well, you can have a simplex constraint. So the sum of the weights is going to equal to 1 for any given x that you put into those weight functions, right? So you fix x, take the sum of the weights at that x, and that sum comes to 1, and that's the simplex. And that's all it's saying is that at any input setting x, there exists a linear combination of models from the model set that will adequately represent your F dagger or M dagger model. So what happens if this is not true? Right? That's sort of what we want to understand. So if there's some, say, x star, where no model actually represents, no model in our model set represents the real world process very well, then we would expect that the BMM prediction at that particular x star is still going to be poor. It's not going to adequately capture reality. In that case, you might think of adding an additional statistical model or statistical interpolator to adjust for the lack of fidelity of your physics models to reality. So it's going to sort of fill in where your physics models miss. And so this is the approach taken in Alexandra's work. And the idea here is that if this interpolator is something like 0 at a given x, then that indicates that there is a collection of models in your model set that's adequately representing reality. Whereas if it diverges from 0, then that's when you know that the set is inadequate. So your model set does not have enough information to actually capture what's going on in reality. And so that can be helpful in identifying where you fail even with a set of many models. Another approach.
So,
yeah.
But
Yeah.
you said that it's the simplest constraint, which is easy to understand. But aren't they supposed also to be non-negative?
Yes.
So this second condition.
Yes.
Okay.
Yes, that's right. Okay, and then another approach is this unconstrained weights or scaling weights kind of approach. And so here, the WK of x's can be any real number, but we'll usually combine that lack of a constraint in terms of the values W of x can take with some sort of prior that prefers that the weights live in 0, 1. So it's sort of like saying, well, we'd like you to be something like a simplex kind of solution if you can find a simplex solution, but we'll allow you to diverge away from it if that makes sense for the problem that you're trying to fit it. And so if you have weights that satisfy the simplex for some x star, then there should be a linear combination of models in your model set that adequately captures reality. But when the weights don't satisfy the simplex, here the BMM prediction at x star can still be good. And basically how this happens is that the WXs will scale the model observations you have in your model set to capture the actual trajectory of the real world process that you're trying to fit. But you'll see this in terms of diagnostic as this diagnostic for inadequacy in your model set. You'll see it as the sum of the WXs diverging away from the sum to 1 constraint. Right? So you essentially don't force the constraint, and you check whether it satisfies the constraint afterwards. Okay, so that's sort of like two different ways of approaching the same problem. And so this is the approach that John takes in his method. Okay, so that's sort of like the overview of the methodology. So any questions about that? Okay, so we'll talk about the software then. So Tawaret. So here's just a diagram to give a sense of how it works. So it's all object-oriented Python code, and there's basically two base classes that you need to know about to understand how it works. So there's this base mixer class, which is the general class upon which particular model mixing methodologies will extend to implement their particular methods. So for instance, we have this trees, base mixer class that extends base mixer to handle the tree-based approach that John does. There's this linear mix class, the bivariate class, and the multivariate, which is Alexandra's class. So this defines sort of a well-defined both interface for the user, but also a well-defined interface for implementers if you want to implement your own model mixing methodology. So if you wanted to do that, you would just go and look, yeah.
So kind of going back to where if you have to have an interpolator to agree with your data, or in the case where your weights are unconstrained and they diverge far from 1 to agree with your data, do we expect that to be predictive for different data, so to speak, or is it, because the conclusion, right, is that none of the models on our space are actually adequate. So is it kind of just overfit, or is it actually going to be predictive?
So usually when you have the divergence away, it's an underfit.
Okay, right.
So if it's fitting well, it should, you either have a linear combination that fits well, or it's putting more and more weight on one model in that kind of subregion that actually captures the reality. So it's like that model works here, right? But when none of them work, that's what you're sort of like, you'd like to know. You don't want it to tell you that something works when actually nothing works.
So like what you're taking away from like the model may not be that like, oh, it actually reproduces the data, but you're actually taking away like, oh, this region is inadequately described by our set of models.
Yeah, so this is like a really good question, because there's multiple layers here of inference that you can actually think about. If you just have one model, then all you care is prediction, and classically you'd do a post hoc analysis, right? So you fit your model, maybe look at residuals, and then see like, oh, I can see that I'm missing a bunch of trend. This model's not very good. And what this allows us to do in complex situations is sort of make that more analytical and more automated. Yeah, so you can have the performance of the individual model, the performance of a set of models, and then the weights are telling you where these models are good and where they're not, and if there's any regions where no model is good, and then you can back extract like that sub-region of the input domain. Oh, I got nothing here that works. Why is that?
Right.
So these are sort of the layers of questions you can think about exploring in that when you look at the posterior of such a thing. Okay, so right, so we have this base mixer class upon which you would build your own, right? Everybody here is going to build one, I'm sure. Just like, stop talking so we can build our own model mixer. So this is where you go. And that'll give you the kind of the user interface, but then also the interface that you need to implement as a developer. But then we also have this base model class, which essentially is like a wrapper for the models that you would use, for the models that the user would use in, say, doing a BMM experiment, right? So they might choose to say, so here, like what I did is this is the user code, right? It's like you're doing an experiment up here, and the red lines are the ones that are actually maybe being used in this person's particular experiment. The dotted lines are just saying you could use all this stuff, right, if you wanted to, but maybe this person just decided to use Alexandra's multivariate BMM mixer class, and they used it with these particular models, right, those 4 models. But they didn't use these models. Maybe these models are completely unrelated physics problem, right? And they took those 4 models, and they took the multivariate mixer, and they got their observational data, and hit run, hit play, and they got it. So if you want to, also study a particular physics application, then you would wrap up your model in one of these base model objects. And that could be, a posterior prediction from surmise, like an emulator kind of thing, right? Or it could be literally, if you have a cheap to evaluate physics code, it could be just that code evaluated. Okay, so that's the Tawaret kind of structure. So again, it's a Python interface to do all these BMM kind of things. Right, it provides a kind of unified interface for both the developer and the application users. And so far we have these 4. Well, we have these 2 implemented, and these 2 are implemented to some degree. Okay, so that base mixer class, again, these 4. Here's the basic methods, or the sort of the collection of methods in that class. Methods in bold are maybe the minimal set that you'd have to implement depending on your particular model mixing methodology that you're doing. You might implement all of these, or you might implement a subset, but you'll probably implement at least the bold ones, such as predict and predict weights. Right? You want to predict the quantity of interest, and you also want to predict those weights from the mixing. And here's sort of a description of all those methods. So evaluate, say, just evaluates the model to get a point prediction. Evaluate weights is similar, but it'll just get one evaluation of your weights from the BMM. If you have a sort of map kind of model instead of a sampling-based model, then you use this map to extract the map estimate of model parameters. Predict, return draws from the posterior. Predict weights, again, is going to return draws from the posterior for the weight functions. Then you can do things like draw the prior and draws from the posterior, and other things you want to do, like set the prior distribution from your particular BMM methodology. Train is one that you'll definitely want, because that's what actually runs the fitting of your BMM. And then there's some kind of standard plot functions that you may want to look at. Some other details on Tawaret. So again, we support a variety of scenarios. So you might be using MCMC in your mixing methodology. You might not be using MCMC in your methodology. So if you're using MCMC, the default mixer is buildy, but it's easy enough to specify your own. So for instance, in our tree code for John's methodology, that uses a very specific MCMC, specific for trees, and so it doesn't use any of the sort of built-in Python samplers. And then multivariate, for instance, uses no sampler. So there's a variety of implementation, flexibility that's available there. Here's sort of like just a general structure of what the code might actually look like when you're using these. So first you would define your model set, and we'll see how we do this in just a second. So I'm just going to leave that blank for a moment. But we'll define our model set, and then you would go ahead and create an instance of your particular BMM methodology that you want to use. So for instance here, I'm initializing a multivariate mixer using the models that I defined in my model set, and then whatever other parameters multivariate needs, you would just email Alexandra and she would tell you at any time of the day. And then you would set your prior distribution. If you had a prior distribution to set, for multivariate you don't, but if it was a different one, you would use that. And then you would hit the train function to actually get it to train the weights for your mixing model. Once the training is done, then you can use predict, add say some test inputs to actually draw posterior predictions of the process you're studying, so of that Y process. And you can also run the predict weights to actually extract also the posterior distribution of the weight functions as well. Again, evaluated at a, say, a grid of test points. Right? And then once you have these sorts of information, then you can do a variety of summary calculations or plots that you might like to do. So you might want to plot the mixed fit of your model. You might want to plot the sum of the W's to sort of identify, right, where there's sort of interesting things going on there. So that's all sort of maybe user-specific what you would actually do. Okay, to get that set of models, we have to use that base model class. And so there are some that are defined in the Tawaret repo right now. So for instance, these models here are originally from the sample package. So those are the ones that appear in Alexandra's work. These polynomial models are the ones that appear in John's work. And then these Coleman models that appear in so that'll give you some examples. Like if you want to actually go and do your own, you can just look at how these were actually implemented, right? How these wrap the particular models you're interested in, and then kind of copy paste. And so for the base model class, you're going to at least want to be able to evaluate, right? Calculate a point estimate from those models. But you might also say need to, if it's a posterior predictive kind of thing that you're using, then you might want to set the product for how that thing is calculated. Okay, so the way to think about this is that simply base model is like a wrapper class that wraps around whatever, say, physics simulator you're interested in studying, or set of physics simulators you're interested in mixing. Right, and as I already said this before, it could be that these are deterministic codes, or it could be, say, some posterior predictive draws from surmise. So here is an example of actually defining that class of models, or that set of models. So here I import from Tawaret those polynomial models, and then I define two particular models based on these more general functions, which take some arguments to specify particular forms of them. So F1 and F2 are the two models that I define here, and then I create a library object, dictionary object to actually define my set of models based on these two Fs that I defined earlier. So that's the thing that we've then plugged into mixing Okay, so that's the high-level overview. Of course, we'll get into much more detail and actually trying things out in both Alexandra and John's talks and their methodologies. You can also read their papers, which I've provided the links for on here if you would like. So it's like a lot of exciting progress, I think, in this area this year with the BMM stuff. And then we should have some more exciting developments, I think, on the density side by Dan and Kevin as they get further into their research on those methods. And then finally, the docs are available here at the Dan's GitHub page right now. So if you want to look at, say, further details, you can go to that website and look around, or you can email all 4 of them. We'll be happy to help. Yeah, all the credit goes to them. I don't do anything. I just say that all the credit goes to them because they've been doing all the great work implementing this software stack. So it's really great. Yes, that's everything for the overview. Any questions before we end it off? All right. Was it Alexandra first?
Yeah.
Yeah.
All right. So I know we're the first session after lunch, and everyone is kind of tired. So we're gonna wake up by doing some kind of, in my opinion, simpler case. So we're gonna get from a one-dimensional case of model mixing with this method, and then John is going to take us through a 2D case. So hopefully in this one we kind of figure out how Tawaret works, figure out how model mixing works, and then when we get to John's case, you will be more than prepared to do 2-dimensional. Okay, so I'm going to do this a little bit like Daniel O'Dell and Pablo Giuliani did, where I kind of let you loose after a couple of minutes to explore this notebook. But I will go through a little bit of how it works first, how the models look. This notebook, if you'll look at it, is very long. That is because only about half of it is in this tutorial. All of the stuff that says Gaussian processes is at the end. If you want to look through that on your own time, I do not expect us to get there. But if you are interested in how you would actually put an interpolant into the model mixing, then there is like a whole section at the end for that. But what we're going to do, what we're going to do first is look at just mixing 2 models together and not using any interpolant, not using anything in the center, just looking at 2 different models, what they look like when you just apply the multivariate model mixing case. So, as Matt did in his workflow, I'm just going to repeat, we're going to define some models, plot them, look at the model mixing results after we apply the multivariate method in Tawaret, and then look at the weights to see what those are trying to tell us. So I'm just going to, for a couple minutes here, talk about the models. So these are the 2 different models that we have. So what we did was we took this 0-dimensional 5-4 theory partition function f of g at the top. Don't worry about what that all is if you don't. We're just going to look at exactly what it looks like graphically. But so what you'll see there is that these are modified Bessel functions, but what I can do is expand this f of g function in 2 different limits. So if you take an expansion of g, then you'll end up with this fs of g, as we call it, for small g, or weak coupling expansion. So you'll see that this is a power series in g, and I will show you on the plot in a couple minutes that this is asymptotic, so it is becoming less and less convergent as I add orders to the series. If you look at this fl of g, that is an expansion at g equals infinity, so 1 over g, I have a convergent Taylor series. So that one is getting better as I add more and more terms to the series. So this is a little better if I show it graphically. There's some coefficients here. Just one thing to note is that the small g expansion, as we call it, is, I think, only, yes, it has only even powers in the series. So if I go to this link, and you guys can also do this, I can show you that as I add more powers in the red curve, you'll notice from here, you see it is slowly backing off of the true model, so the true model is in black. And as I add more and more powers, so I go all the way up to about 20 here, it is very, very divergent compared to the blue model, which is this large G, or strong coupling expansion, that is getting more and more convergent as I add powers. But what we're going to do is say, what if I only have 2 of these? What if I don't know anything about this integral, what this exact true model is, and I want to just take maybe 2 to 3 powers of each one? So then I end up with, as you could see, and later on you'll be plotting this, is that you end up with these curves that have very, very large regions in the middle where you don't know anything because these two expansions are going towards infinity or minus infinity. So what we were thinking is, how do you possibly model mix these so that in the region where both of them are failing, can you get a result that is reasonably close to the true model? So what I'm going to do from here really quickly is scroll down to the point where I actually kind of define how this works. So what you're going to see as you go through this notebook in a couple minutes is that, exactly as Matt said, you form these Gaussian distributions from your mean, which is the model that I was just showing you, and these variances that you can determine. So we did this a little bit like, if you've heard of it, like an EFT expansion, you figure out what the next truncation order is based on what your what the powers that you have look like. There's a little bit more in this notebook. You don't really need to worry about that if you don't want to. If you do, it's all in our paper, and I put a link up here, and there's a lot more information right here of how you do that. But just say you have these variances, and you're putting them into this Gaussian distribution for each model, and then you want to combine them. So you use this f-dagger function like Matt was talking about. So we assume that this is going to be a Gaussian distribution of Gaussians. So all we're doing really is going through and combining the means and the variances in this Gaussian way. And then you'll note later too that the weights come from looking at these precisions or inverses of the variances. So this way they are all normalized to 1. So this is basically how this multivariate case works, because you can see that I put in there the sum of f of k. You can have more than just 2 models. We're just going to do 2 for now. There is a challenge exercise at the end if you are feeling up to it to add a 3rd model and see what happens to your weights and your f-dagger function once you plot that to see how this changes. So I'm going to go back up to the top, I guess, and I will leave something up here. There we go. Okay. And then everyone can start going through the notebook. Like I said, at the end, there are challenge things that say go back and change a few different things and see what happens. So we'll see if we get to that, but we're going to let you go and explore some model mixing. And as last time as well, please talk to each other. It makes it much more fun.
Yes. Disentangling between these two models. Do it here, we get to things, and all of it is it's a concern. I think this would be better. Yeah. Very good. No, I get it. Thank you for extra. These need to be nice. It works. Yeah, it works for this description. And where's the back of the test?
Yeah.
Okay. I remember when Alexandra did this factoring. Let's go on. I swear to This is the whole reason why we chose collab. It's because Dan named it, so, but from what I can tell, it's because this creature It was like a bunch of different stuff. He was like, so we tried that was the pros and like two different things. So
I was just about to say.
I talked to them. We're accepting design. You could like.
Image generating AI stuff. Oh, that's a great idea.
Oh, yeah.
Did everybody
Back in like first year.
Yeah.
It's right on. It's on. Bring up the second.
Yeah, so that's
Oh, yeah.
Which this is what you would do.
Oh, yeah. Take the last 10 minutes.
Oh, yeah.
So this part, yeah.
I did it, and then I undid it. There were things that I hadn't done that I was like,
So just
so like,
that was basically.
I guess I was
Identify like a goal-oriented thinking where maybe this is like yes. Class. The widest and then of course make sure that these notations that is
That's right. But the
so I really like that.
it's assumed that was simplex. I don't know where that happened. So that's
Now it's me.
yeah, I'm here.
I am free from my
you said that
travel discussions.
one way successful
Yeah, so I wasn't here.
That
I just,
Oh, for me, the second
Yeah, that's
Oh, so the dash part is
actually,
very serious how to construct a layer.
This is
yeah,
right,
yeah, and then the
They
dot
just
is
can
from
be
all
those
the
ways.
truncations that I get from whatever.
I divide social organization. This is one way.
So we
Whichever way.
verification.
It's wide up here. Yeah.
then it's down.
It's
probably around 0.5.
Because you're going from the.
Probably around 0.5 to it's like I don't know which models, right?
None of this has any use.
And then it's gonna end up at 0 once we get and then the flu rates will be exactly one where it's really good. And it's gonna curve down.
So this is the assumption. This is the assumption in real life.
Right.
And then in the middle, this is why
Back in the day, just
had this third
kind of flavors. But then the downside of that is like no.
Right, but it could also be that someone.
So it took this model to try to do something better than they had. It has been around for a while.
Right. So yeah, when they added the interpolator, that name's then it gets much closer.
Which you made, actually, it's very nicely seemingly very flat. And then, what we also give you just simple model science.
Well, actually this,
Another interesting point,
why, how,
something to
yeah,
do with
why we use it.
So we use this because it's a nice case, so like I really, you could use, but for this guy, it's really nice, kind of nice because this function does this thing, like goes back in the middle where there is nothing that you can really say, because both models give some values. So in a lot of physics cases, you'll find stuff, right, that like stops at a certain point, but then these are kind of nice because they overlap, so then kind of figuring out how to
Is the black
yes,
okay.
so I've used
Okay, so this is just the
it's the
model.
true model.
It's the model.
Yes.
And then you have this.
Yeah. Right. Because you want to know when you first start developing this theory, you want to know what like this is. And then you can go test it on stuff you don't like. Yeah. But however, the point is that you come back and you do some more stuff. Like you can go back and change the truncation and see how that changes. And then you can go back and add more models and see how that changes.
Break up under.
those models,
It's not
models identical. Provide the same data.
And how the.
So you need to establish on which you will make the
Yeah. Were you calling?
Yeah.
I was explaining it. The outside. We'll say.
I answered yes. Okay, let's do that. Now ask me now. Here you are. What you have observed is a of what? Like, I thought that the way that you work here is large protons, and the way that you were always bound from the next order. It's kind of like later example.
Yes, so it's.
In which case, this number has no statistical meaning in its interpretation.
Yeah.
You know, there is no statistical
Oh, that's an
framework
excellent point.
that tells you that this is a percentage.
Oh, yeah. Yeah, okay, I'll go ahead and do that. So that's not supposed to be there.
And then this is not a variance itself. Like, when you say
So it's
somebody with a statistical background will be like, this means there is a statistical model that tells you that this is a confidence interval. I haven't done anything.
that is kind of so
I think that's a Python thing, like if we when we run a function in Python,
But they are not associated.
it's 4 things, but we only want the last 3. That's how we do it in Python.
So just saying ignore the okay, great, thank you.
expected next word.
Correction?
Yeah, correction.
I 100% agree. But it is the different ways that you try to find the language.
you have a model.
I do remember, That's fine. I am saying it because I remember a lot like I said that I actually like a lot where I don't exactly remember what he's doing when he's brought in the next leading order operation. So the first thing is he has a band with a big count, and the next one a band that looks a bit other But then these has a something that is accurate or not. I am happy that whether or not these intervene with each other.
And that's someone else now. What's this action? Point the dash. But now you say, okay, if I want to rate, what's the prediction? You would say,
Oh, yeah. Right, so 95% of flying.
90% of region is mapping
But when you do the
and then if I move
yeah, so that's
I get this at 2 seconds and a left, I get that.
I don't know.
Oh, that's too light. That's then I would have to say middle range.
How good each model is.
And then the front end, as you can see, that means I'm very sure that the
Higher weight than that.
as I make it,
Once you get to when one, I don't know it's really better.
it could be.
One has to be
Those intervals are short.
Some
Yeah.
If you had the right one, and you need somebody to estimate how big
Right, so you can do that. What about let's say you don't use that, then you don't get understand it.
not whereas blue is maybe just go in and that's once I have that, the more interpretation going on.
Yeah, exactly. The more active my interpolator is, the so the interpolator is really active in the middle range. But then on the edges, the interpolator basically. There it is, right here.
What's the kind of the first one But I really do
So this would be the case when
you know what I mean? He's basically that, oh, okay, I am super certain that the tree is here, it's here. But it's not true because I keep adding things and it's going to start
Based on
That's tricky.
Because that I know why by having an initial parameter.
Because I've been mentioning, you're going to be like 5 care. But it's going to be where if I were to solve kind of a like, yeah, like eventually what I expect is that something narrow doesn't be encompassed by all of them.
Yeah, I know.
That's how I want it.
And model of how we do things.
I know.
Maybe it's this one.
Because I'm trying to do like physics, but then I don't know anything about the absolute point.
Should you read it that? The model. We might also have.
The idea is that we figure out, but theoretically I wouldn't have that, so I need to make some assumptions.
That's what it is there.
Yeah, yeah, assuming that I'm like supposed to be doing like where I know
Have you watched
That's the one over.
Yeah, I'm gonna like. Alright, so we have two things to do. This is the first one, and I'm gonna hand it to John to do the more interesting one of two. Alright, so you want me to just do it on here?
Yeah, so I will just quickly introduce the stuff I've been working on, and then we can feel free to dive into the notebook and finish up with Alexandra's as well. So the problem that I'll talk about right now is two-dimensional. So with Alexandra's, you saw one-dimensional x, one-dimensional input. We're trying to essentially interpolate between those two models. And now what happens if we have a two-dimensional input space? So one of the analog, or one of the methods we've implemented in Tawaret involves a flexible non-parametric method known as Bayesian additive regression trees. So I'll just give a quick overview of what that method looks like, quick overview of what a tree model is, and we can maybe dive into it. And then introduce the example, and we'll dive into the notebook. So our BART BMM method is going to take this mean mixing approach. So as Matt had introduced, we're going to be mixing at mean levels. So we have these mean, this prediction simulator. We'll combine them with these input-dependent weights. Now, in our approach, these weights are not going to be confined to a simplex. They'll be constrained via prior or regularized via prior. There's going to be no implicit constraints set on them. And now these weights, wk of x, the question is their input of or it's a function of x. So how do I specifically define that relationship between x and the weights? So what we do is introduce tree bases to help model that relationship. So here I'm just going to show a quick example of what does a tree look like. So if you're maybe not from statistics or maybe not too familiar with, say, data science as well, you might not be too familiar with a tree structure. So that is, on our panel on my right, and you can see. So here, a tree is essentially, you can almost read this as a map. It's partitioning the input space. So what this says is if I have an x, I'm going to start at the top of the tree, and then if my x1 is less than a, I'll go down to the left. And if my x2 is, say, less than b, I'll go down to the left one more time, and I'll end up in this terminal node. The terminal node is where the predictions happen. So you can see above, in the hierarchy of the tree, that's where you're kind of splitting up this input space in a meticulous manner. Then you get to the bottom of the tree, and that's where I'm going to get these predictions. So in the bottom of the tree, that is where I'm going to get the predictions of the particular weight functions. So you can see the tree on this in panel A, and panel B is the corresponding partition of my two-dimensional input space. Now, the big thing to take away is these mu1, mu21, mu31. Those are the estimates of the weight functions for our particular problem. And if I'm looking at this, if I'm looking at this, say, bottom left corner, and I have an x1 that's less than a, I have an x2 that's less than b, I'm in the bottom left corner. So that means the prediction from the tree model for any x that lives within this particular subspace is going to be this mu11. So you can think this is like a tree model. The output is essentially this piecewise constant function. So if I have one tree, I have this piecewise constant representation. So you might think that might not give me a great prediction of a weight function. So the idea is, let's get m different trees, as you see here. And then what we're going to do is I'm going to fit m different trees. They might look something like this. They might look like something completely different. Either way, I get this very flexible representation in a flexible way to partition my input space. I get these m different trees. I add them all together, the outputs of those trees, and I get my corresponding weight vector. So that's the idea of very flexible non-parametric Bayesian approach. And then just a couple of key properties is, these weights, we're going to try to confine them with the prior so that they prefer the interval 0, 1. However, they're not going to have to sum to 1. They're not going to have to strictly live between 0 and 1. And you can see, some of the specific properties. So I'll just scroll here, and if you just look at this first panel of the weight prior, each color of the curve represents maybe a different value of the hyperparameter I can choose for the variances that you can read up on above this figure. But you can see each color is a different prior, an implicit prior I might have for my particular weight function. So in some cases I might be, say in this orange curve, yellow curve, I might be centered around 0.5 and rather constrained between 0.2 and 0.8. But maybe in the red curve, a different prior I can choose is still centered at 0.5, but has a quite wide distribution. So there's different things you can tune in this model depending on your particular problem. So just a last quick note before we can dive into the actual notebook is just to talk about the models we'll be mixing. So this is a two-dimensional example. I'm just using different polynomial models or Taylor series expansions of these trig identities. So here our f dagger, this true function, is going to be defined as f of x equals sine of x1 plus cosine of x2. Then I'm going to consider mixing f1, which is Taylor series expansions of sine and cosine centered about pi in both the x1 and x2 space. And then f2 is these different Taylor series expansions centered at negative pi. So it's going to be a similar flavor to what you saw with Alexandra's notebook, to where I have models. They're very accurate in some part of the domain, yet in other areas of the domain they're going to, the accuracy is going to degrade. So with that, you guys are more than welcome to jump in and let me know if there's any issues with installation or anything along those lines. Sure.
one which is in the second table, which is by us. I'm going to be careful with the reference.
Yeah.
So now I know that I'm very sorry. Yeah.
How big should be your
I don't know how well it works.
Okay. I was thinking.
Yeah.
It'll matter.
So that's next slide was also the
Yes.
I told them I was like,
You may have.
But therefore,
Anytime soon. There's a lot of physics. Strong coupling, weak coupling, high temperature, low temperature. You usually have models for each of those. What do you do with it? And that's something that actually prepared. Someone who's playing with these hot approximates, we can do it kind of interpolation, trying to do a statistics way of interpolating. Yes. Things that are going on in practice. Nuclear equation of state.
Yeah.
Target for so high density particles you have QCD, turbulent QCD, long way away at the low you have something like chiral effect or whatever else you have. So you have things that are presumably good at two ends, and now you want to connect them. Particularly like to see is there room for phase transition that's one that generally
But in practice, they're so far away.
well, the question is what do you do? I so those are just theory things. We are now in some data from experiments. Lambda's going to set the scale. So something I think usually higher density from low energy for the ion cooling. But for this one,
Getting it from effort back, yeah, so I was back. So,
it's all working on transfer.
I guess so.
Then you can add it
It
back.
seemed to be a pretty good time.
Doing their basically theory. Figured out according to your expectation for how the breaks down. No, it's expansion. Therefore, judged by the next term in this year, you have the top data. But you may also have some data. And then put everything one overlapping, but mindless one bring up the very lowest higher best prediction. Another thing is this that actually integrates over
Details.
scattering.
That's details. Yes, these are two separate parts. Two separate parts. So they're not actually.
But you know the
Don't have to really have. I should have picked that color.
You don't know yet.
Basically, the way prior is as you can see, like choosing some nice K is going to give me a more flexible kind of
Insight or understanding.
and choosing by new or like new and lambda is just to show, we can also support that less.
I may not be able to. Just gonna warn you.
Try to mix these to interpolate.
I was like, was there?
Draws a line there.
Yeah.
Take into account how the errors are going. May not be perfect.
It's not.
We'll make a bigger
Yeah,
mistake
and
once we accrue.
plugged in.
So one Gaussian implies
Yeah,
it's a bit constraining in the sense that
that's a good question.
the tail style.
Well, I haven't done, yeah, because I was like,
Probably but there's a possibility of way. So then you would use something more and it looks like a bell curve, but
I
it's
suppose I could have let them
Well,
go.
right.
it's probability that it's not something.
And that's dependent on.
Well, part of the analysis.
Yeah, but then if it drifts,
That's just a natural choice. I would think that
right, if it drifts the way his case. So I guess like he's kind of doing like a
assumption.
that
Doesn't mean
Yeah.
sensitivity allows it doesn't mean that every prior is equally good.
I guess like
I wanted to see one more.
So
I don't need him to.
I would have thought it was
that bothers people.
whenever you have a test, there's
There,
Yeah,
I would say everything's yeah, so that's what happened. Yes, I think there was something to do.
Why is there
Particularly, what are the big gap, right? 40 times. A couple of times down here.
I don't know.
When you say it's surprising, so
I guess
having a framework for
It's somewhat better if you phrase a little bit better the potential.
yes.
So what you guys take my model.
Yeah, so I was thinking, so we had
Kind of like a scale.
Daniel talked about using Bayesian where I would think about temperature and what.
There are some subtleties involved with how you're doing a calculation. Some order in this.
That, because I'm thinking about it, and I'm like, I was thinking about it earlier, and I'm like, maybe like
Pressure.
stuff that they do on the one side.
Different people have done it, maybe they've done slightly.
Yeah, the people who maybe QC their analysis is terms of typical potential. Right? So the energy is going to be potential that defines the energy scale. Right? And alpha defines the time. Right? So they usually talk 2.4 GeV, 2.6 GeV. And it's like 40 times like million dollars.
It becomes a tricky thing, so I think it's running that makes a lot of work consistently to a different order.
But also,
It's not a pure perturbation theory. Not linear capacity. It's running now to some order.
I might have T1.
oh,
But then like, 1,000. It's maybe
This corner is extra bad because like there is some
More original.
go way off both.
More of like
so
that goes to
Yours is a little bit
So,
better
for
than mine
instance,
because that's not
find
dark.
Yeah.
MCMC I
It's
don't
true
know.
is why I agree.
Oh, it's model
But I guess if you would guess it would be more interesting to look at like astrophysical data.
Yeah.
At least that
So,
No, actually, it's really still kind of
Sorry.
Let me know if you questions or comments.
that is
Sorry, there's like this argument.
Good. Just looking at the weights for this. So
QFT is done in
neither model.
unless you want to create transform. Don't say where it's at.
That's exactly. Yeah, yes, that's exactly where. Yep.
oh, yours is.
Yeah, ours is.
Well, my model is.
Yeah, no, I didn't,
If you want to suffer, then go ahead.
I'm messing around with cage.
Oh, okay.
It's similar, but like more rigid than other structures.
So I know you're also not okay with
Radiation transport, so tracks the
Stepwise.
This is why last time we did the cross.
Yeah, I think so.
I haven't defined it. So,
We go to 33, 34. Yeah,
you're in for like once everything's done. Usually a value things.
I don't know why we're
So
so
we were
function.
exactly.
There's a really good choice.
It goes down the side. More than it's asked what is the way for is someone here that is because this is a way this is a way for the person.
I'm getting this
So
stuff from
this
Philip
stuff
and
here
other
happens to
experts.
and right now this is a very simple tree. My weight function has three possible values. This one, and this one. If you ask me here, I give you this. If you ask me here, I give you this. Here, you give you this. Here, I give you this. You know, it's a lookup table. So it's a elaborate table. Well, you have a whole ensemble. And you have a whole ensemble. And the idea is that they go further down the way that makes it.
What's the difference? Why are we higher?
I should. Well, I don't want to run anything. But I was like,
It's the same model that's put on there. You can still
So
take.
in here you will suppose that this is L and J. So I want to predict the
Yeah.
binding energy. But yeah. Yeah, yeah, then maybe. No, I think I knew it. Sorry. Yeah, so he was saying that.
What do you mean? Bayesian model.
I was just correcting the thought was
Interpretation. Yes, you have any questions?
this thing. So like the models don't have to be really they relate to each other. So on the third.
Yeah, like a mixed math prediction.
So it have the same sample in the sample here, but in the output.
Right, I mean, I can do, there's no discussion now.
Yeah, just fluctuations in the way that the
So I'm just trying to
thick experimental data.
conceptualize the tree model. So in a sense, is it learning sort of where the cutoffs are? So those are the parameters essentially.
Yeah, so you can think of, so a tree is, it seems like an abstract parameter, almost that you're really that you can update. And when I update the tree, I'm gonna update maybe where those splits are, what the age is. Yeah.
That makes sense.
And then piggyback to the question like Matt, were you able to run everything?
Yeah.
So you can some of the weights and things like that. Yeah, so this kind of based on your question earlier, just what happens when inadequacy. So you can see like the weight's pretty close to 1 and everything was nice and the model starts covering things. But out here, so the prediction is going to be okay. So I can still get a decent prediction, but the inference on my model set is going to amount like that.
That's kind of my chemistry. Where that question was like, it seems to be misleading if you don't
Exactly.
are at a different swing.
Exactly. So that's where it's like, right, because if you change the prediction, you think, oh, it's great, maybe, yeah. Then you use your integrated perhaps somewhere. Yeah,
Then so what's
misguided. Yeah, so if you put everything together, then you get that. The other thing, easier case.
different data sets.
Very good.
So the whole issue of model competence.
Many other cases.
In principle, you would like to
There is something like
Exactly, that's what
using basic different layers. You have to identify the set of data which we use to differentiate Yes, and then after this, you will realize that out of 20 models which but SVD is beautiful because it gives you also the combination. So you know that combination of either 1 and 0, right, is meaningful, and other combinations, you know, the weight combinations.
They did not do this one.
No, they don't.
They talked about the same problem, but they did not do something that's sophisticated.
But this is something which is absolutely important prerequisite, right, for those model mixing. Otherwise, you don't know the single 100.
I did. I tried something before. But suppose I have all 20 models, and all the physics they have is all the same.
So that's why we say it's difficult.
So they're all going to be missing. Start is closer, and so we I have prior
Sum everything together.
that still has to get
Sum of that gives me implicit
I guess the model
And you would like to measure
So if we think of it in general, if I have X and say X is normally distributed, Y no idea. If I add those two together, I get a distribution variable. Same idea.
then you will not have to figure out all those numbers are going to cost you and those densities. is when you have high problems and right?
What could be?
Yeah, no, when this won't count.
Clearly not. So to me, then the region of 3 or 4 is productive.
No, I know. But if I have a state my model, I know I should invest tomorrow. 20% because of this check. I know all this thing has to be. And that uncertainty is but that's what I also.
You cannot estimate.
Well, maybe you can, but you need to put it in. The way you're talking about it.
No.
Yeah, put it as a systematic error. There's something important there, you know.
That's the problem,
When I add this to the
None of the measures that you use
one point is,
seem to have kind of.
This goes to our
find that
way, or guessing more people would guess more accurate. Cow swallowing.
Because some of those default values. Okay, everyone. We're just about out of time. So I think we just want to open up for any questions about model mixing in general.
Yes.
So the function or the figure you have with the tree and then the partitions, could you pull that up here?
The top one.
Do you have a smooth transition from U21 to U31, kind of like a gradient across that boundary?
So in the most basic form, no, it would be a piecewise.
Okay.
So you'd have a jump, just calling it that particular transition point.
When you say basic model, so could you elaborate on what could be done?
There's some extensions with BART in general, different ways to smooth those things out. There's some that we're currently working on. So can't really get into grave details now just because that's active. But you can look at, say, in the traditional BART model, there's also the analogous soft BART model. And same thing with soft decision trees.
maybe you could comment on whether this BART type approach particularly effective?
So BART is going to be effective whenever you have maybe these higher dimensional cases and maybe a little more complex functions, because it's able to actively learn the different regions of the input space and say where one model is good versus one model is bad. But yeah, definitely a higher dimensional setting. And also
Quantify higher dimensional.
well, starting here when we jump to 2, 3, 4 dimensional input space, it just kind of depends on your different applications. So maybe in nuclear physics, might be limited at 2 or 3, but maybe in more general settings of physics or what have you, then maybe we can jump it higher. But that's something we need to look at. Pablo?
Sorry if I miss it, if you explain it and I miss it. I understand that whenever you're doing the Markov chain Monte Carlo part, you're basically exploring, given the data that I have, the likelihood, how many trees I can build, similar to the tree that I'm starting with, that more or less agree with the data equally well in a statistical way, and then you use that to see other places that you haven't had an evaluation, and that's how you construct your mean and your uncertainty around. My question is, what are the rules for moving in the tree space? Do you say, I cannot go deeper than a level? What are the, literally I'm thinking like a chessboard, what are the allowed moves that you can have each time you jump from one tree to
the other in the jungle.
Right, so we can start simple. Just to quickly answer that. So say, for instance, this is my tree at one iteration in MCMC. I may try to update that with what's called a birth step. And what that means is maybe I'll pick this Ada 3.1 terminal node and introduce another split here. So instead of having 3 terminal nodes, I would have a tree that I'm proposing with 4 terminal nodes. So it's little moves like that, just having these little changes to the current tree structure that will give me a slightly different prediction. And if that, based on, and you would accept or reject that with say a Metropolis Hastings step. It's just, if you're updating a tree instead of just updating a specific individual scalar parameter, for instance.
But then what is preventing you from overfitting? The
Right.
priors that you put in?
Yes. So you would have priors on that are going to try to regularize how deep this tree can get, things of that sort.
It reminds me a lot of Bayesian neural networks. It has a different functional structure, but of this idea of I'm going to be playing around different architectures and changing weights here and there with a prior that is trying to regularize the thing so it doesn't just overfit.
Right.
Thank you.
I'll just add 2 things. So for the higher dimensional, a completely different application, but one of my former students did civil indices for BART. And so that's like a way of detecting is this variable active or not in this data set or process. And he did some simulation studies where he would add dummy, so inert variables to the data set, and he was adding in like 50, 100 inert variables, and it was still detected flying stuff.
Real high.
And then the second one is for Pratola. I think a lot of people in the Bayesian tree literature would say that Bayesian neural networks remind me of Bayesian trees.
I can imagine, yeah.